Okay, if anyone can decode what's going on here, Andrea will offer you a job or a position.
Get in touch. We'll talk about job opportunities if you can actually decipher what's on there.
Let's do it. Hi, I'm here with Andrea Morello, who you've no doubt seen a previous video about quantum computers. We've done a 1.5 hour
We
video of
did.
us talking
It
about
was
quantum computers.
very comfortable back then on the Red Velvet
on the
Lounge in
Red
my
Velvet
house.
Lounge. It was
But
lovely.
this time is gonna be, we have to move a little bit more, but hopefully it's gonna be even more exciting because you can see, it's actually very lucky, you can see both a quantum computer experiment completely open and accessible and a quantum computer experiment all closed up, cold and vacuum and so on, but functioning, so with functioning quantum bits. Right there, ready to look at.
Awesome. And where are we today?
We are in the Fundamental Quantum Technologies Laboratory at the University of New South Wales in Sydney, Australia.
Australia for the win. All right, and you're the head professor here. You're in charge of the group?
Yes, I'm the professor of quantum engineering in the School of Electrical Engineering and Telecommunications at UNSW, and I'm also one of the key people who have set up the world's first undergraduate degree in quantum engineering.
Fantastic.
So we're actually
Still the only
teaching
one?
this stuff.
Or
As far as I know, well,
following?
there's another one in Germany, yes.
Yep.
And things are popping up in the US, but you know, there's a growing consensus that this thing needs to be addressed because there's a lot of jobs in quantum technology that need to be filled up by qualified people, and such qualified people do not grow on trees.
Got it.
So someone like us need to do something about it. So that's what
So
we do.
usually it's part of another course. It's not a dedicated course. It's part of an EE degree, some branch of an EE degree.
So in the old days, people were able to take quantum engineering courses as elective within an EE degree, or they would come through a physics degree and they would do quantum physics through the physics degree. And then lots of people did physics and EE as a dual degree, so those people were quite well sorted. And another really killer degree is, for example, quantum engineering and computer science.
Ooh.
That, as you'll see in a
That's
moment,
where the money's at.
that's where money's at, and that's where
think the money's going to be at.
yeah. No, that's really killer app. Yeah.
Got it. So you're going to show us a real
Yes.
quantum computer, or is this mainly a research rig? What is
Well, this is definitely a research rig.
Right.
Look, how can I say this politely? Okay, let me just not go out of. There is no truly useful quantum computer in the world. The most advanced, the most useful quantum computers are also still used for basic research, for hardware development, and also, though, to help people learn how to program quantum computers. Probably if you ask me today what is the most useful application of a quantum computer, is for people to learn how to use them and program them. So that's kind of where we're at.
In anticipation that the hardware will eventually become practical.
Exactly.
Got it.
What we do here is we develop from the ground up, cradle to grave, as I like to say, from the design, the theory, the nanofabrication, the measurement, the analysis of the data, everything from beginning to end, silicon-based quantum computer chips. So what we have in these devices, this one is actually about to be removed. This is, let me call it a 2-qubit quantum computer. It's a single phosphorus atom, and the 2 qubits are one atom of, well, one nucleus of the phosphorus atom and the electron that is bound to that phosphorus atom. That's a 2-qubit system. In this other setup, we have an atom of antimony. Antimony is a heavier, bigger atom. It's 2 rows down from phosphorus in the periodic table. So it has a bigger nucleus, and the nucleus has 8 quantum mechanical states. 8 is 2 to the power 3, so that nucleus alone is the equivalent of 3 qubits.
Nice.
And then there's the electron, and makes it 4. So technically, that's a 4-qubit system.
Yep. We've done that. We've covered all this in the previous videos. So, yep.
Awesome.
Here to look at the hardware.
All right, let's look at the hardware. So if you type quantum computer in a web search, what you will find is something like this. This is not, of course, a quantum computer itself. This is the refrigerator that cools down the quantum computer chip. The quantum computer chip is actually down there. So what you see here is a copper box which is there to protect to shield electromagnetic radiation, both for actual, electromagnetic noise reduction, but also to prevent any high-frequency photons, which are carriers of energy, from hitting the chip and heating it up. Right? So the rig itself is called a dilution refrigerator. It's a refrigerator that uses, in fact, it uses quantum physics to reach 0.01 degrees above absolute zero.
Wow.
That's right. So maybe we want to take a step back and see how the whole thing sticks together. In the end, this will be a vacuum enclosure. You can see the remaining vacuum cans there at the back, right? They've been just removed. And you can also see those silver-plated shields, right? There are the white painted, those are the external vacuum cans. And then the silver-plated shields, those are radiation shields. So those are to prevent the warm surfaces on the outside of the refrigerator from radiating hot black body radiation into the inside, which would provide a heat load and make it difficult to cool down the inside to the temperature we want it to go down to. So the system works in, let's say, two stages. First, there is what's called a pulse tube cooler, which you can probably hear. This machine is off, but the other one is on. You hear this ch, 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 ch. That's basically a cycle of compression and expansion of helium gas, which gives a cooling power that allows the plate that you can see if you look from here. So this plate here can go to about 4 degrees Kelvin, so minus 269 degrees Celsius, or 4 degrees above absolute zero. So that is cooled down by, let me call it crudely speaking, the 10 kilowatts version of the refrigerator you have at home, right? Your fridge at home, to keep the food cold, also has a little compressor and a gas, and you hear it going zzz.
It turns on periodically.
That's right. And this is like the giant version of that, using helium gas. The reason it uses helium gas is because helium is the only substance that never solidifies, even at absolute zero temperature. It remains, so it goes liquid at 4.2 degrees Kelvin, but it then it never solidifies unless you put 30 atmospheres of pressure on that. There's a whole story. I could keep you for hours on that, but let's not get distracted.
How do you physically verify it's at that temperature, or is it based on the fundamental physics? You know it's at that temperature.
We have thermometers all the way through, and funnily enough, those thermometers are just chip resistors. So a lot of the little surface mount resistors that you use in normal electronics, they are actually optimized to have a very flat temperature coefficient around room temperature, right? You build an electronic circuit and you want it to be, temperature stable in case your circuit changes temperature a little bit. And so these resistors are made out of some special oxides, and they have a temperature coefficient that changes sign. So the resistance goes more or less flat around room temperature, then increases again if you heat them up again, and then increases again if you cool them down. So it's like a parabola. So if you cool them down to very low temperatures, you can take I just know from memory, a 1.5 kilo ohm resistor will go about 20 kilo ohm when you are at 0.01 degrees above absolute zero. So there are some absolute calibrations that are done with various melting points. Yeah, there's traceability, there's ways to verify that. You calibrate these simple chip thermometers against these other reference thermometers, and then you place them at strategic points along the fridge, and then you have just a resistance bridge that measures their resistance.
Can we physically see those in here?
Yes, they are here. So they're actually held. These are the heaters, actually, the thermometers. See, they're just attached to some little copper poles. They're tiny little chip resistors cased into a copper thing and then attached. And then there are these little looms. You see those ribbons? They're basically twisted pairs. Put it in a loom, and then they go all the way up, and you connect to this instrument. I'll show you the one on this rack, which is the same. So this thing here is a resistance bridge, is an AC resistance bridge.
Nice.
So with this thing, you can measure the resistance of those little chip thermometers with a power dissipation of order picowatts.
Nice.
Right? That's important
beautiful.
because the cooling power of this refrigerator at the lowest temperature is about 10 microwatts. So you need to make sure that anything else you attach there doesn't start pumping power, otherwise it heats up.
Of course, yes.
And so the resistance measurement itself has to be very, very low power in order to be set up.
What is
And
that
then you
wrap
see-
around that post there? It's like
That's
it's
a copper.
braid.
That's thermalization.
Oh, thermal.
That's
thermal
right.
Equalization braid. Or?
Exactly. So the braid is the loom. So those are the signal wires for the thermometers.
Oh, okay.
But the thing is, because they come from room temperature, and they are conductive wires. So by the Wiedemann-Franz law, if you have an electrical conductivity, you also have a thermal conductivity.
Right.
So you want to make sure, and these things are not copper wires. These things are they're usually manganese or constantan. There's some lousily conductive thing, low thermal
EMF,
conductivity.
low thermal.
That's right.
Yes.
And so at every stage, you want to hook them up to a copper post and wrap them around and soak them in something called GE varnish, which is a special kind of, it's insulating varnish, but it has some decent thermal conductivity, and it's like a goo that you use like a glue. And it thermally anchors the wires at the various temperature stages to make sure there isn't too much heat coming down. And the same is done, as you can kind of see, with the coaxial cables. So these ones are semi-rigid coaxial cables that are used for the high-frequency lines.
Yes.
And you see they all get broken down at these posts here. And so there, the body of the cable is attached to a bulkhead. And that bulkhead is gold-plated and thermally anchored to the plate, so the cable gets thermalized there. The problem with coaxial cable is that the inner conductor is actually not very well thermally anchored, right? So that's why you always give them loops, because by giving loops, the Teflon dielectric that's inside will pool when you cool it down. If you have ever tried putting some Teflon cable in a nitrogen vessel, it will shrink a lot. So this thing actually pools, and that pressure helps a little bit with thermalizing the cable. And then, let me see if I have it here somewhere. Where are we? There should be an attenuator. Yeah, it's probably somewhere here. let me see what I can see.
Attenuator, is it
Yes,
RF attenuator?
an RF
or-
attenuator, that's right.
Right.
The role of the RF attenuator is to actually thermalize the inner conductor. So it cuts off some of the high frequency radiation, and it provides a galvanically conductive path between the inner conductor and the ground, which again, by the same principle, is also a thermal link, so that the inner conductor gets cooled down a little bit. And then the thing you see here, this is something we built ourselves, designed and built. It's a filter box. So this is a box that contains RC filters and LC filters, and again serves the job of thermalizing and filtering away all the high frequency radiation by the Planck-Einstein relation that the energy is the Planck constant times the frequency of a photon. A high frequency signal carries photons with a lot of energy. So you want those photons to not be there unless you really need them. So everything about doing low temperature experiments is a game of, we do need high frequency signals for certain purposes, but where we don't need them, we have to filter them out completely.
Got it. Are there any vibrational problems like triboelectric effects from your Teflon coax?
Oh yes, I'm glad you asked. I'm glad you asked. We are the world experts on this.
Oh, really?
Yes, we are. So you see these black cables here?
Yes.
So those are graphite coated. They're black because they're graphite coated. These ones.
Yep. Yeah.
They're basically flexible coaxial cables. They have copper nickel inner conductor, a Teflon dielectric, a coating of graphite, and then a braided copper nickel outer conductor, and then, very importantly, another Teflon gasket on the outside. So what happens is this. Once you cool down your coaxial cable, the Teflon shrinks, right? And so take a semi-rigid cable like this. Once the Teflon shrink, the part that's inside the rigid outer conductor can just move around as a result of the vibration caused by that cryocooler.
Yes,
Is that right?
Yeah, yeah.
And so we actually analyzed this, and we found out that this is like a noise source with an internal impedance of 100 kilo ohm. So on the high frequency lines, which are 50 ohm impedance matched on all sides, that doesn't matter, right? The voltage division between 50 ohm and 100 kilo ohm means that the signal you get here is basically nothing. But on the lines that we use to measure the transistor, which is what reads out the quantum bit, the transistor itself is switching between 100 kilo ohm and open circuit. And on the other side, there is a transimpedance amplifier, which some people incorrectly call a current amplifier, but you know what I mean?
Yes.
We don't, yeah, we know it. That has a very small input impedance. So that voltage source with 100 kilo ohm internal resistance will create a current that goes straight into the input of the transimpedance amplifier. So we'll see all of that. So these cables have been designed to kill that problem, and they do so by having, one, the graphite, which is a solid lubricant, and two, the outer Teflon gasket is like a corset. It also shrinks, and it keeps it all in. So we have a whole very detailed paper from a few years ago where when we first started using these systems. So these kind of cryogen-free dilution refrigerators, they're relatively new. In the old days, people used actual liquid helium, like a bath of liquid helium to arrive at 4 Kelvin, and that means there's no vibrations there. Once we started using these things, that's when the whole hell broke loose, right? So, oh, no, how do we deal with this? And so that's why, actually, we also bought this specific vibration isolation setup. This is quite extreme.
Yeah,
so you see,
there it is, yeah.
This is a very solid frame on which rests a very thick aluminum plate on air suspensions. This is what holds the actual refrigerator. Then all the components of the pulse tube cooler, the ones that make the noise and vibration, are on a separate frame. Right? The two things are decoupled, mechanically decoupled. And then all the pumping lines, there is a pump that circulates helium gas. They are held on a separate frame that has a 250 kilograms concrete block, and the lines are cast into that concrete block.
Nice. That's the effort you had to go
That's the whole thing.
Wow.
Funny enough, you can't buy this thing anymore. The company doesn't want to sell it because it's an absolute nightmare to put it together. You have these, half a ton frames. You have to line them up to a millimeter, right? Oh. So the installation engineers were going absolutely crazy. So we were very lucky we managed to get some of those models while they were still willing to make them.
So you're not moving labs anytime soon?
No, not these ones at least.
You don't move.
Not these ones, yeah.
So we're running a experiment in there at the moment, and you said that you've got I'm here on the lucky day. Yes. What experiment are you running? You're doing groundbreaking research at the moment.
Yes, we are. Now, it's going to be a little bit complicated to show you the actual groundbreaking side of things because it's really quite advanced quantum mechanics. But my student Steve, whom I would like to invite on camera here, he has set up a couple of little scripts to show you how we do the basic operations on these quantum bits. So first of all, I'd like to dispel this myth, right? People have this idea sometimes of the scientist as, the guy with a white lab coat and the thick glasses there in some dark bunker, handling, little knobs and stuff, because there's nothing like that, right? Nowadays, doing an experiment means writing, scripts that control a bunch of instruments, okay?
You're just a script kiddie.
Well, look, there is a part of the job that consists of, setting up that whole thing, connectorizing, making the device, testing it, connecting all the instrument, making sure everything is calibrated. But once it's all up and running, it's basically run from behind a Python script.
How often do you tweak the set, like the physical setup? Or
Not often. So when we find the perfect chip, it may stay in a fridge for a year.
Right.
There is so much
Research you can do
research
on that
and new science to be done with one prototype chip that it often stays cold for a year. Some have been cold for 4 years.
4 years?
Yeah.
Wow.
Yeah.
Wow.
Whereas sometimes that fridge, for example, is the one we use for more of a fast turnaround. So we'll try something for a couple of weeks and then we'll swap chip, but it just depends.
Can you cycle them? What happens if you thermally cycle them? Does that cause issues? Can you turn them off, or do you have to leave them?
They tend to come back. So if you do a thermal cycle, what happens is this. These devices are single charge devices. Okay, we are addressing single electrons and their spins. So the presence or absence of a single electron charge within, let's say, 50 nanometers of the charge that we want to look at will slightly change its behavior. So it just takes one electron to be stuck at a dielectric surface in the vicinity to slightly shift how this device behaves. But in the end, when we go and look at the spin qubit, the actual object that carries the quantum information, that one is pretty solid. So the thermal cycle and other electrical effects will shift a little bit where we have to go to observe that single electron. But once we have it, it tends to behave the same way because an electron is an electron. Within, there's a subtleties, but yeah. So maybe I'll just talk you through this one. This is a map that was taken just this morning.
Yeah.
So what you see here is in color scale, it says DC voltage. That's the DC voltage that comes out of the amplifier chain. But you can think of this as being the current through the transistor. Huh? So bright yellow or green means high current. By high, I mean half a nanoamp.
Yep.
Blue means zero. Dead.
Okay? Because your sensor is basically a one MOSFET which you guys have designed,
modified.
And
so
manufactured.
That's right. It's manufactured and designed by us.
Is it a high electron mobility transistor? Is that?
No, actually no. The
it's
electron
not?
mobility is not that great.
Okay.
Yeah, is not a particular high electron mobility. What makes it special is that instead of being a continuous MOSFET channel, there are two barriers across the channel that isolate a puddle of about 100 electrons. And then the conduction, instead of being a continuous conduction path between source and drain of the MOSFET, has to go by quantum tunneling through those barriers. So any electron that wants to flow through the transistor needs to arrive at the barrier, quantum mechanically tunnel through the barrier into the little puddle of 100 electrons, and then tunnel out.
But that's based on probability.
Yes, but that probability can be controlled.
There's the secret source.
Yes, that's the secret source. So that probability can be killed off completely such that there is no current, that's the dark blue you see here, for most situations. And then as you scan the gate voltage on the transistor, you will find a situation where basically for an electron to be on that island or not be on that island, there is no energetic difference. So the electron can be there or not be there, it makes no difference.
Right.
And so that is the only place where you get current, because you can get an electron that goes onto the island, and then once it's there, it can escape again. One at a time. And then another electron goes onto the island, stays for a bit, and escapes again. And by tuning the transparency of those tunnel barriers, we can tune the current we get through. So we can tune the probability to give us the current that we want. So this is one of the simple constants of nature. You know that the electron charge is 1.6 10 to the minus 19 Coulomb. What that means is that you have 6.24 times 10 to the 18 electrons per second in 1 amp.
Yes.
Right? Now, no one remembers that, but if you're people like us, you do remember that, because it means you get 6.24 million electrons per second in a picoamp, right? So a picoamp of current means there is 6.24 million electrons per second going through. So if you want to get a picoamp of current, we actually want more than that, but just to keep the number simple, if you want a picoamp of current, you need to tune the quantum mechanical tunneling probability for an electron to come on and off that island such that there are 6.24 million electrons on average per second that make it through.
Got it.
Right? So what you're seeing here, if you just scan this gate along this axis, you see these peaks of current, right? So every time you move from here to there, so let's say you go up here, you're going more positive. So more positive voltage makes it more desirable for an electron, which is a negative charge, to be on that puddle of electrons. So between every peak, you've added an extra electron to the island, one by one. You can actually count them.
Why are they not
Equispaced?
consistent, equally spaced?
Yeah,
Yes.
because that island is not very large. So if you made a larger island, they will be perfectly equispaced.
Got it.
This island is actually small enough that you get a combination of classical Coulomb charging energy. So to put an electron, a single electron on a capacitor of capacitance C, you need to pay an energy E squared over 2C,
Yes.
right? Now, this thing is it is a capacitor, right? It's a little capacitor plate
Everything has
capacitance.
Yes.
But in addition, it's also a quantum confinement potential. So you're getting a bit of a mix of classical Coulomb charging energy with quantum mechanical level spacing. So that's why they're not quite completely uniform. There's a lot to unpack in there, but anyway, the key point I want to draw your attention to is this. Look, for example, at this point here, this line. You see? Here we've got all these peaks. They all follow each other, not quite regularly for the reason we now understand. But then if you move left here, these are two different gates. Like there's more than one gate around the transistor. There's a few of them. It breaks. The whole pattern breaks and shifts. Right? What's happening there? What's happening there is that as you go left, again, the voltage goes positive this way. So as you go more negative on this voltage, you are making it less desirable for electrons to be there. And at some point, and that point being exactly here, there is one electron somewhere that just pops out of wherever it is and doesn't come back. So the whole pattern shifts. It goes into the drain. It goes into the drain of the transistor. It just vanishes out. The point is, that electron belongs to a single antimony atom that we have implanted into the silicon chip. So we've put in there an antimony atom. That antimony atom is a group 5 donor. It's an N-type donor, right? When you go to low enough temperature, instead of donating an electron to the conduction band, it holds the electron there. It behaves like a hydrogen atom. So the nucleus is like a positive charge and the electron is the negative charge that's bound to it. But here is like having a hydrogen atom in the middle of some electrodes that allow you to rip the electron off from that atom. So here, on the right-hand side of this break, there is an electron bound to the atom. As you pass to the left-hand side of the break, the electron gets popped out and just vanishes out into the drain.
So you dope it with one atom?
Yes, one atom.
So there's only one atom in the whole...
Well, in this particular device, we have about 20 atoms, and you can see there's more than one of these breaks.
Okay.
Right? So there's one here, there's one here, then one here. There's a few of them.
Right.
We actually do have the technology to put one and only one atom. We are right now in the process of making qubit devices with deterministic single ion implantation.
So that is desirable to have a single...
It is desirable to scale up. So for the purpose of early experiments, it's actually quite nice to have more than one because you can kind of find the one that's in the right spot. You know, like for early experiments, it's actually convenient. Long term, if you want to actually build a deterministic large-scale quantum computer, you want to have one in every spot and nothing else around.
Nothing else. Yep.
Because it gives you more freedom. Yeah.
Qubit
So
block.
one in every cell of the array. So think of the quantum computer as an array of physical qubits, like, classical computer chip is an array of transistors that act as, 0-1 switches. So there you will want to have one at every site. But for these early sort of prototype devices, it's actually quite convenient to have more than one. But there's not a lot of them. There's maybe 20 of them in total. This is where the magic happens, exactly at this corner here.
Right.
Okay? So what happens there is that if you were in zero magnetic field, if you sat right there at that corner, that electron would have the same preference to be on the atom and be off the atom. So you will get this situation that it's actually a random telegraph signal, which many electrical engineers are familiar with. You would have an electron that jumps on and off. The electron actually comes on and off that island of electrons, and then from there it may go away into the drain. But it first got onto the island, so it just goes back and forth.
It physically goes back and forth?
Physically goes back and forth.
So not the probability? We're
No.
not talking probability, right?
Well, when you're talking probability, you can actually see it on the screen. We'll see it in a moment. You can see when it does so by the switching of the current in the transistor. Right? So when the electron switches on and off, you're basically switching from being in the dark blue. Let's go up here where it's a little brighter. From the dark blue to the green. Right? Which means zero current to finite current. Now, when does that happen? That's the randomness. And that's why it's called random telegraph signal. It's not a square wave.
Right.
It's got some randomness in the interval between the switches.
Width. So it's almost randomly pulse width modulate.
Yeah. But there is a time scale, right? So you have slow random telegraph signal, fast random telegraph signals, so you can actually show. Steve, you want to show? Yeah.
And this is true random.
That's true random. No, that's true random. That's real random. Yeah.
So what we can do is, okay, we just go to this point and zoom in this point and show a live scan. Okay.
Yeah, we can show a live scan right there. Yeah. So zoom into that area.
Okay, so we're just running a Python script at the moment.
Yeah.
So what you can see here, okay, is this line, okay. And then, okay, you can see the blips, okay. We have the spikes, and this is what Andrea just mentioned. You have the tunneling event of the electron onto the donor of the donor.
Right.
Yeah. And you see, it's pretty random where they happen, right? And also the duration. Some are a bit longer, some are really sharp.
Yeah, I noticed that,
So that's a 2D live scan. This is done reasonably fast with just too fast sort of sawtooth waves. Yeah.
But you're doing a research experiment.
Yes.
Right
So this is,
today.
let me put it this way. The way we address and encode quantum information in these spins is by magnetic resonance. Okay? Now, doing magnetic resonance on one spin is actually not harder than doing it on a quadrillion spins, like what happens to you when you go and take an MRI scan.
Yeah, right.
So that technique, I'm not saying it's easy, especially when you do it in a refrigerator like this, there's all sorts of complications, but the real hard part is to read out a single spin, right? Once you have readout, once you have a physical access to the physical property of that qubit, the rest, I'm not going to say it's easy, but it's kind of, the floodgates open, right? So this is what we got done in 2010. It was the first spin readout in silicon done right here. That really opened the floodgates for everything we were able to do after that.
Right. Got it. And you're working on silicon because you think that's going to be the most practical in the future.
That's one of the reasons. The other reason is that silicon is a semiconductor that is made out of 3 natural isotopes, silicon-28, silicon-29, silicon-30, of which the most abundant is silicon-28 that has 0 nuclear spin. So whereas silicon-29 has a nuclear spin of 1/2, so it's actually a slightly magnetic nucleus. Because the quantum information is encoded in the magnetic state of the electron and the nucleus, any other nuclei that carry a spin act as sources of noise.
Yes.
So we have access to specially isotopically purified silicon material where those silicon-29 spins have been almost completely eliminated. So that gives us some people call it a semiconductor vacuum. Right? These atoms implanted in silicon are really almost the same as being atoms in vacuum. despite being in a semiconductor with, you know, gates and nanoelectronics and stuff we can connect to.
Do these silicon-29 isotopes, do they cause a problem on regular silicon
No.
chips? No, it's
No, they
only
wouldn't.
for this quantum world.
Well, little curiosity. So silicon-29 for us is a problem because of its nuclear spin. There has been research, I think probably about 30 years ago, in the classical semiconductor electronic industry to see whether a purified silicon-28 material without the silicon-29 and the silicon-30 would have better thermal management properties. So silicon-29 and silicon-29 not only has a spin, but it also has a different mass. So if you look at how does heat propagate through a crystal,
Right.
I'm oversimplifying here, but it's almost as if as the difference between electricity propagating through a pure metal versus an alloy.
Right.
Right? So
it.
silicon having 3 different mass isotopes, the crystal vibrations which carry the heat are modified and made more complex by the presence of 3 different mass isotopes. So it is true that if you have a single isotope silicon crystal, it has a better thermal conductivity. So in the context of, you know, super high density chips, you would imagine, oh, that'd be great. It turns out that improvement in thermal conductivity is most significant at low temperatures, going by memory, probably minus 100 Celsius or something like that. At room temperature, it's not much.
So you're talking
Some
like
percent, maybe,
astronomical type
like
things.
yeah. So there's no commercial reason to go through the effort of doing that.
Got it.
But people looked it up. People actually tried and did experiments because in principle it does change thermal conductivity.
Interesting.
That's because of the mass, not because of the spin. We care about the spin. Yeah.
And so when we read in this information, we put up that live view again.
Yeah. Okay.
So it's all happening regardless of whether or not you start this script. It's all you're just actually measuring it.
No. So we're always measuring the current.
Right. Yeah.
But what's happening here, the script makes 2 voltage sweeps on the gates.
Right.
Yeah.
Got it.
For example, if I just stop this one, and you can actually see from the picoscope or the oscilloscope, this is what happening again at this point.
Yeah.
So in this case, you don't need to switch 2 voltages. But just sit at the radar point, and then you have the blip event.
As the thing I was telling you before, if you just sit there, you will see electrons just randomly hopping on and off. Now, this is tuned in a place where it's much more often on the atom than it is off. So it very rarely pops out. But for the most part, it stays on the atom.
So when you read it out, you've destroyed that information. It's no
Yes.
longer...
Okay. We haven't actually done readout yet.
Oh,
so
you
to
haven't
do the
done
readout,
okay.
now let's see.
So
Do you want to do?
non-intrusively...
No. I'm just looking at the charge. Well, in a sense, I'm reading out the charge state.
Right.
I'm reading out where the charge is.
But there's
okay?
no useful information.
That's not my
gained.
quantum bit.
Got it.
My quantum bit is the spin. So the spin is a quantum 2-level system. There is a spin down and a spin up energy level. And we place this thing in the refrigerator at 0.01 Kelvin and in a magnetic field of about 1 Tesla, which is a big magnetic field.
big.
The Earth's magnetic field is 50 microtesla, to give you a sense. So that the energy difference between the spin down and spin up state is more than the thermal energy of anything in its surrounding.
Right.
Okay? And I don't know if you want to have a look, it's actually over there from the other setup that's been dismantled. You can see the superconducting magnet that is used to create the magnetic field.
Okay. So that's
So this is it's a solenoid of superconducting wire. It goes superconducting at about 10 Kelvin.
What's the material makeup of that wire?
This is
No?
niobium titanium.
Right.
It's an alloy, niobium titanium. So it's a big solenoid. It has an inductance of about 10 Henry for the electrical engineers among us who know how big that is.
Yes.
It's a very big inductor. And it's run by those power supplies there, so it takes with about 100 amps of current, you get about 6 Tesla magnetic field from this magnet. Now, the interesting thing is that because it's a superconductor, you don't need to keep it powered up all the time. So you can charge up the inductor to the current that you want, and then there is a superconducting switch that you can use to short circuit the coil.
Right.
And then you can turn off the current, and that supercurrent will flow on forever.
Yes.
That's actually what happens at the hospital. When you go to see an MRI machine, you will not see a power supply there.
Right.
Someone, the installation engineer, came one day with a rack of power supplies, charged up that magnet, disconnected and walked away and went to charge up the next magnet at the next hospital.
Got it.
Right?
But if they remove the power, they're screwed.
No,
Well,
if you
they
remove
use
the cooling, if you
which is
remove the
power.
cooling, you're stuffed. And so for those of you who are interested, you can go and look for magnet quench on the internet.
Magnet quench.
Quench, yes. So magnet quench is what happens when there is a hot spot along the superconducting wires such that the wire goes from being superconductor to being a normal resistor.
Yep.
And once you get that, it starts to dissipate, and so it's a runaway process because it heats out the parts of the wire that are next to the hotspot, and that hotspot propagates until the whole wire goes normal. So you have a 10 Henry inductor charged with 50 or 100 amp that is suddenly becoming a normal resistor.
Right.
In fact, a fairly, this is not a high conductance wire. Niobium titanium is an alloy. It's not like copper or gold,
Yeah.
And so there's a huge amount of power dissipation, and it boils off the whole helium bath in which the magnet is immersed.
Right.
So go on the internet, look for NMR magnet quench, and you'll see this thing where this big puff of cold helium gas blows out because the whole thing has
Nice.
gone resistive and blows it up.
Got it. That relay that shorts out the superconducting relay that shorts out the coil, what happens to that if you short it out while it's
No, it's actually not a relay. That's the interesting part.
Oh, okay.
All that is.
Right, I'm physically
No.
thinking
No. It's a very good. You're a very good question, Dave. It's actually a piece of the exact same superconducting wire put across the inductor.
Yeah.
But in normal operation, when you want the switch to be open, you wrap a little resistive wire around that piece of superconducting short to make it go normal. So that thing will be a few ohm resistor,
Right, which is nothing compared
which
to
is in
zero.
parallel to zero, so nothing goes through it,
Yeah,
right?
right.
Whereas if you stop heating it up, then it goes superconducting,
Yes.
so now you have a fully closed zero resistance circuit.
Got it.
Yeah.
Okay, that makes sense.
Yeah, and that's built somewhere in there. There's a little.
Oh,
Yeah,
right.
yeah. So you will see. Yeah.
Oh,
So you
yeah,
see this
yeah,
little
that's
thing
a
here?
couple of little cables. Okay,
That's the cable that
Right.
feeds that little heater to
Right.
turn the switch on and off.
Got it.
Yeah.
You got some serious ground bond in here.
Yes,
Is
that's
that
a
is
building
that
ground.
thing? Oh,
It's a
just-
thing. Yeah, no, that's a clean ground. So we want to have all our instruments connected to a ground that is separate from all the noisy ground that all the rest of the building
course,
runs
yes.
off. So these are big copper strips that go to a stake in the ground that's been cast with a special electrically conducting gel and so on.
Wow.
And so
Okay.
all our instruments are on isolation transformer, and it's like a star connection to the ground, to that clean building ground.
Got it.
Just little power
And,
hygiene.
EMI is not an issue.
It is. I mean, of course, this thing is itself a Faraday cage, right?
Right,
So,
of
and then the other thing, you've already seen this,
Yes.
we try to shield as well as we can everything. That's not to say that EMI, no, you still pick up stuff. These things are so sensitive. You see things. I'm not saying that we have complete and utter, EMI protection. But the thing is, we need to put signals in, right? So there are certain experiments where you only have very low frequency signals, and people build shielded rooms, like fully shielded rooms. Like the whole system is inside a shielded room. All the cables go through a copper feed through, and you can do all that. But we have to run 40 gigahertz microwave signals into the system. There's all sorts of fast pulses. So in a sense, the EMI from the environment is not even the biggest problem given the kind of signals that we pump into the system. So we try to do the best we can, but you know.
And you have to use the 40 gig odd frequencies due to
the value of the
value
Planck constant. Right?
So, yes, right.
This
it
is
has to be very precise.
Yes,
Otherwise,
absolutely.
you're going to be
Yeah,
out.
so this is one of my favorite things to when I teach my quantum engineering course. You know, I just tell students there are some numbers you need to remember, like your date of birth. One is that 1 picoamp is 6.24 electrons per second. That's the electron charge. The other one is that 1 Kelvin is 20.84 gigahertz.
Oh, okay.
That's the ratio of the
yes.
Planck constant to the Boltzmann constant. So an energy of 1 degree Kelvin corresponds to a photon of frequency 20.84 gigahertz. And that 1 Tesla is 1.34 Kelvin on a free electron. So if I put a magnetic field of 1 Tesla on just a free electron, that energy splitting is 1.34 Kelvin in energy, and it's 28 gigahertz in frequency. So now you know why I need this. So we normally operate at 1 to 1.4 Tesla. But the higher the better. The more separation you have between the energy levels. Buying vector microwave sources above 40 gigahertz becomes a very expensive exercise, and also the microwave engineering of that is really starting to become...
They would make those to order. You probably couldn't get off the shelf at that point.
Yeah, so it starts to get really challenging. 40 gigahertz is enough. So 40 gigahertz is, what, 2 Kelvin in energy? We are at, realistically, 100 millikelvin, 0.1 Kelvin. So, you know, 40 gigahertz, and that corresponds to 1.4 Tesla magnetic field. So it's funny how just the ratio of constants of nature gives you the shopping list for what you need to do to run an experiment like this. I don't have that, you know, I don't get to choose. Those constants of nature are what they are. That's why I need this beast, right?
Yeah. And I think it's important to note that this is not the operating frequency of the quantum processor, which is only down in the 1 megahertz or something.
Way slower, yeah.
Way
Actually, we might see how fast it goes in a moment. Yes. Okay, let's go back to we got a little diversion here, but let's get back to... Okay, so what we're doing here is this. We are applying microwave pulses at different frequencies. You see the frequency axis here, it goes from 38.6 to 39.2 gigahertz. So what we do is this. We start with the electron, electrochemical potential at a position, in that corner where I showed you before, in a position where only an electron spin down can go onto the atom, whereas an electron spin up doesn't have, there's not enough energy to populate the spin up level. That's why we go so cold. If we went warmer, then you would populate both 50-50 probability. That's what the refrigerator is for. At this temperature, we can, with almost certainty, populate the spin down level. Okay? Then what we do is magnetic resonance. We apply electromagnetic radiation at the exact frequency corresponding to the energy difference between the spin up and spin down states. And when we hit the right frequency, that electron spin down gets excited to the spin up state. Once it does so, it has enough energy to escape the atom again and give us the blip of current.
Right.
And make the transistor switch. So what you're seeing here now, this is the scan. Again, you know, bright means high current, blue means low current. As a function of the frequency, and here we're kind of repeating as we go. So you see there are some specific frequencies at which you get a bright line. What's happening there is that there is more than one frequency at which that electron responds. Why is that? Because there's a nucleus attached to it. So that nuclear spin, this is in particular, and you'll see it in a moment, we populate them all. This is an 8-level nuclear spin. It's antimony 123.
Right.
It has a spin 7/2, so it has 8 quantum levels. So it has 8 possible orientations. And every orientation of the nuclear spin corresponds to a different effective internal magnetic field that is applied to the electron that shifts the frequency at which it responds. So depending on the nuclear spin orientation, we will get a different frequency at which the electron responds.
So you won't get that for the phosphorus one.
No,
You'll only
phosphorus will
the
get only
four.
2.
2, sorry.
Yes, here we get
Right.
8.
So that would offer greater information density.
That's right. So an antimony atom has 8 levels instead of 2. 8 is 2 to the power 3, so it's the equivalent of 3 qubits in one atom. So what Steve is doing here is basically scanning the electron resonance frequency as he flips the nucleus as he goes, so he can see all the various resonances.
They are perfectly even spaced.
Yeah,
not quite.
almost perfectly, again, for reasons that have to do with they're almost perfectly evenly spaced. Yeah.
Got it.
They would be exactly evenly spaced if you went in the limit of infinite external magnetic field.
Got it. Okay. That
So
makes sense.
if you turn the field lower and lower, you will lose the ability to measure it. But imagine you could do it, you will see that these things become more unevenly spaced for reasons.
Got it. And then they start overlapping, and you can't tell the difference. Is that...
Well, what happens is that you start to entangle the electron with the nucleus.
Ooh.
Yeah,
Quantum entanglement.
Quantum
Yeah,
entanglement.
we don't
Yeah.
go there, do we?
So well, we do sometimes, but in this specific case, we want to work in a regime where, if left in peace, the electron and the nucleus are disentangled, so that the electron acts as we call it an ancilla, is an ancilla device to read out the nuclear state. Right. You see, what you're doing here, I mean, when you think about it, you're actually watching the quantum state of a single nucleus. By seeing at what frequency the electron responds, you know which way this single nucleus of antimony is oriented among 8 different possibilities. Just think about it. We take it for granted, but think about it for a minute. You're watching, you're watching a current through a MOSFET, right? And by doing so, you are watching the magnetic orientation of one nucleus.
Yes. And you're getting all this information from the IV curve of a single...
Not even the IV curve, just for the current. So we set it up at a specific voltage, just the instantaneous current.
Because one electron is
enough to switch the
conduct
transition
that.
on and off.
And you can easily measure that because it's in the order of...
Yeah, it's
several
nanoamp.
nanoamps.
Yeah, it's
Right.
nanoamp.
And
It's
that's
fine.
easy to measure.
Yeah, it's fine. Yeah.
You can use off-the-shelf stuff.
Off the shelf, yeah.
Yep. Wow. Okay.
Right?
So the information is destroyed when you read it out like that.
Correct.
At what,
So,
yeah,
all right. So let's
You
say...
can't copy it because you can't
Well.
copy quantum information. You can't...
Let me try and put it this way. So let's say I had prepared a quantum superposition of the nucleus being in this state and in that state. Right?
You've set it up that way.
I've set it up that way. And then I went to measure at what frequency the electron responds. I will find only one of them, which means that nucleus, the quantum state of the nucleus, has been projected to the state that corresponds to the frequency at which the electron responded. Right? So given the initial quantum superposition state of the nucleus, there could be 2 frequencies at which the electron responds. I go and interrogate the electron. If it gives me a blip at 39.2 gigahertz, then I know that the nucleus is in the highest spin direction.
Got it.
And so even though before I did the measurement, it was in a superposition of 7/2 and 5/2 spin projection, after I see this blip of current in the transistor, that nucleus is collapsed into that specific orientation.
Got it. Are you running applications on this quantum computer?
No, it's too small.
It's
there
too
is
small.
no
There's just no
application of any
There's no
kind
practical
at this
at all?
scale.
At what scale does it start to become practical?
Well, it's a $1 trillion question. So it starts to become practical, depends what application you're looking at. Let's say that the earliest applications are probably going to be the ones where you use a quantum computer to simulate other quantum systems, such as molecules, for example, pharmaceuticals.
Right. Yes.
So why can't you design a cancer cure on a computer? Just say, oh, this is what the oncologist said I have. I've got this kind of cancer. write a Python script that gives me the drug that kills the cancer. You can't do that. Why? Because whatever, imagine that drug exists, maybe it doesn't, but let's say if it existed, the classical computational complexity of calculating the behavior of all the nuclei and electron in a reasonably complex molecule is far beyond the capability of even the biggest supercomputer. An interesting factoid, one of the biggest molecules that you can, manageably simulate on a classical computer is caffeine.
Oh, okay.
Caffeine is not very big. Look it up. Go and type caffeine molecule structure. It's a fairly simple molecule. And that's because it's a quantum mechanical problem. All those atoms and orbitals and the chemical bonds and how they interact with other things, such as the cancer cells in the body, is a quantum problem.
Got it.
So why don't we use a quantum system to understand a quantum problem? That's the logic of it.
Simulate it and
So for that, you'll probably need, I should know this better, but I'm guessing, okay? Don't call me up on this. Please don't cancel me on the line. Of order some 100 to 1,000 very good qubits. Very good qubits.
What's the difference between a very good and a crappy qubit?
A very good qubit is one that you can run, thousands of operations on without errors along the way. So what I call a very good qubit is a qubit that can be operated on for thousands and thousands or possibly more operations without errors. Now, this is very difficult to achieve in the physical world, in the practice. So what people are trying to set up is some redundancy, where one bit of quantum information is encoded not in one, for example, atom, but in many of them. And there are some operations and measurement sequences that allow you to both operate and change the quantum information on that encoded qubit, but also detect and correct errors as they occur. Now, there's an interesting thing about this. The absolute minimum amount of redundancy you need to have to make any kind of quantum error detection and correction is 3.
Right.
Now, how many equivalent qubits do we have in this atom?
Oh, you've got the
3.
Right.
Right? So that's why this is really exciting.
Okay.
There are some very clever colleagues of mine who came up with ideas to encode what we call a logical qubit, so a qubit that has enough redundancy to detect and correct errors in a single nucleus, instead of having to piece together different physical qubits that are spread out across the chip.
And you couldn't do that in the phosphorus one?
No, there's not enough. There's only one qubit there. There's not enough.
So you'd have to
not
use
enough
multiple
space.
qubits to do the same operation as
That's
you can
right.
do in a
That's
single
right.
qubit.
Here with antimony, we can do it in a single nucleus.
Right. Got it. But is that going to be more complex to manufacture? No?
No, you just change the mass selector in the ion implanter.
Oh,
This is exactly the same as a phosphorus device. If you look at them from the outside, they are indistinguishable.
So why is anyone working on phosphorus anymore?
Well, look, it's easier at the beginning to do the early experiments.
Right.
I mean, I have to say, we are basically the only group that's doing this, right? So
Right.
these experiments are very hard, especially the fabrication is very, very, very hard. What we have here at UNSW is really an amazing nanofabrication facility, which is actually part of the national collaborative research infrastructure set up, by the Australian government very, very cleverly. It's called the Australian National Fabrication Facility. So it's actually, it's accessible, user-accessible fabrication facility. But here at UNSW, there has been more than 20 years of really focused investment in getting the specific tools you need to get silicon nanoscale quantum devices done properly. And this stuff is not easy, it's not cheap. There has to be really a critical mass of people who want to do it, but we have it here. So that's why we're able to make these devices. You can't just wake up one morning and say, oh, let me do this.
That's all right.
Yeah.
Okay. But with the phosphorus one, it's easier. You can, smaller
Look,
groups can muck around
the
with
device is actually the same.
Right.
It's actually the same. So even making the phosphorus one is hard.
Right.
From a nanofabrication point of view. It's exactly the same. Moving to antimony, the microwave engineering of it, in fact, the RF engineering of it becomes more complicated. But even that has been made easier in more recent time by the progress of FPGA waveform generators. I don't think we're going to be able to show you this. It gets really complicated. But basically, to control this 8-level nuclear spin, you need to have 7 radio frequency signals, right? There are 7 differences in energy between the 8 states. So you need basically you need an RF generator that makes 7 signals at different frequencies, and each one of them completely phase coherent. So I need to be able to make a pulse at frequency 1, then a pulse at frequency 2, then a pulse at frequency 3, and then come back to frequency 1 and be in a perfect phase relation with the first pulse I did a millisecond ago. That is actually not that simple, but it is becoming possible now with the latest generation FPGA waveform generators.
Got it.
Yeah.
Very
So 10 years ago, it would have been a real pain.
Right.
Now you can buy a commercial machine. It's not off the shelf. It's a startup that makes machines just for quantum control. You can buy it, and it's already the FPGA is programmed. There are some code instructions you can use, and you can make all these multi-frequency signals all phase coherent with each other, and you can operate this whole large multi-dimensional quantum system like that. Okay, so what Steve is going to show us now is the rotation of a single electron spin. So we started in the spin down state, and then we apply a burst of microwaves at 39 gigahertz. And the electron, the probability of finding the electron in the up state will oscillate. Remember, it's always a probability.
Yes.
Okay, so we start down, that we can do deterministically. But then we start to make a superposition of down and up that has a heavier and heavier weight of up.
Oh.
Until it goes all the way up.
Okay,
and
so
then
it's
it comes
weighted.
back down. It's weighted, yeah. It's
Okay,
it's a weighted probability, yeah.
Okay.
So this is done by applying a burst of microwaves at approximately 39 gigahertz and changing the duration of that microwave burst. The longer you leave it on, the more the electron rotates.
Got it.
So you can see it going all the way from down to up and back.
What sort of period are we talking about?
So we are talking 8 microseconds.
8 microseconds.
Yeah.
Okay.
So
for a
this
rotation.
is for a full rotation. Yeah.
Right.
And so what Steve is doing here is just repeating the experiment multiple times. You can see all the traces. And remember, so this is on the vertical scale. I don't know if you can see it on your camera. It says up proportion, which means how many times you get a spin up. Our measurement is binary, classical. We only get a 0 or a 1. We get 0 current or high current. There's nothing in between. So how do you know if a spin is pointing halfway between up and down? You repeat the experiment 30 times, and if you get 15 times down and 15 times up, that tells you it was in a superposition of 50-50 superposition of being up and down. That's
Okay.
effectively what you have to do.
Are you controlling the period of that? How are you controlling that?
With the power. So if you crank up the amplitude of the microwave drive, this thing will oscillate faster.
Got it.
Yeah.
Right. And that relates to the kind of the effective quantum processing time of a quantum computer?
It kind of does, that's right.
It does,
So, for example, if you want to do a NOT gate
Yes.
on the bit, that will take 4 microseconds
Got it.
in this. So the clock, this will be, you can call it 100 kilohertz clock speed.
But the advantage eventually will be the parallelness of it.
Is the complexity. So you will use a different algorithm to arrive at the result. And
Yes.
that algorithm will have a much smaller number of steps. So even though every step individually may be slower because we're running a 100 kilohertz clock instead of a 2 gigahertz clock, if there is an exponentially smaller number of steps to arrive at the results, we'll still get there sooner. Then we can do the check nuclear spin. Yeah, so Steve has written a couple of scripts that are ready. Demonstration ready.
ESR, is that equivalent series resistance?
No,
no,
electron
it's
spin
not.
resonance. Electron spin resonance. Okay, so you see, this was blue for several shots, and then it switched to orange, right? So that's ESR1, ESR2. What this means is that he was checking all the 8 possible frequencies at which the electron responds. And for some times, it was always this one. Then it switched to this one. And then it switched back to the blue one. What it means is that the nuclear spin has switched between 2 states.
I'm amazed that you can do this with just like a current.
And the basic signal is what you see here on the oscilloscope screen. It's just those spikes of current.
That's nuts. Because you know what frequency and timing you're exciting it at, and it doesn't have to be that quick. The fact it needs to be at the 40 gigahertz or the 28 gigahertz due to the fundamental constants, but you're controlling that.
Yes, let me go back to something we discussed before, which is why silicon, right? I told you we can get silicon-28 enriched material that removes the silicon-29 spins that give you noise. Now, if I was doing the same experiment on a natural silicon chip, like the ones you have in every phone, this wouldn't work. Because the spin would lose its quantum state quicker than I can address it.
Got it.
So the reason I can take my time and have that clock speed of 100 kilohertz, so do that rotation in a couple of microseconds, is because that spin knows its quantum state and remains, its precession is coherent, so the phase of the precession, the frequency at which it precesses is constant over time scales of hundreds of microseconds.
Right.
If I did that in natural silicon, it would be in the nanosecond range.
Oh, okay. So it's in theory possible,
but very hard, very hard.
Right.
We made here the very first quantum bit in silicon in 2012, and that was in natural silicon, and that was a hero experiment. We had to put a lot of power down to do the things really fast, and you could barely see the oscillation. Once we moved to the isotopically purified silicon, it's paradise.
Magic. And how does that relate to the magnetic field strength?
It doesn't. It does. So the magnetic field strength only tells you at what frequency needs to be the signal that flips the spin. But you were asking me before about, is this a high electron mobility transistor? Mm-hmm. So many of them are made in 3-5 semiconductor, like gallium arsenide, right? People have made spin qubits in gallium arsenide, but again, they suffered the same problem, in fact, even worse. Gallium arsenide has only isotopes with a spin. Both gallium and arsenic have a nuclear spin. Oh. So in that material, even though from a charge point of view, from an electrical conduction point of view, it's super clean, you can get this super high mobility transistor from an electrical point of view. From a spin point of view, they are very noisy and very hard to operate.
Got it.
So we much prefer having a silicon MOSFET where the mobility is not that great, but the spin properties are fantastic, rather than the other way around. And so again, just I want to, especially your viewers, to sink in what's going on here, just watching. And this thing is literally just counting how many blips we have here, right? Yeah. This is a counter, renormalized between 0 and 1. When you see the thing switching, you are seeing a single antimony nuclear spin switching direction.
Wow.
That's happening live before your eyes. And that's just by counting how many blips you're getting there.
And the other 7 or whatever you've got in there?
They're all low. We actually check all of them, you see?
Oh, okay.
We're checking all 8 of them.
Right, okay. Of course.
And that's important. There's only ever one of them that's high. Right?
Right.
You can only ever see it in one quantum state. All the other ones are low, and one of them is high.
Got it.
Right?
Interesting. So you'll never see 2.
You want to show the nuclear Rabi? Okay, so now we're doing the same thing we did with the electron before, so to make the electron rotate. Now we do it on the nucleus. Now here, this is done at a much lower frequency. The nuclear spin has a much smaller gyromagnetic ratio. The gyromagnetic ratio is the frequency at which the spin precesses in a certain magnetic field. So for an electron spin, that's 28 gigahertz per Tesla. 1 Tesla magnetic field gives 28 gigahertz. For a nuclear spin, well, it depends on the spin. In fact, every nucleus has a different gyromagnetic ratio, and that's what people use in chemistry to do chemical analysis with nuclear magnetic resonance.
Oh,
right?
Right.
They can tell what's in a molecule by looking at what frequency
I wondered
the spin
how
responds.
I've never looked into it.
Yeah,
Right,
that's how
that
it goes.
makes sense.
Every spin has a different gyromagnetic ratio. Antimony has a 5.55 megahertz per Tesla gyromagnetic ratio. So here it will be running at what, 7.5 megahertz more or less?
555.
Yeah, 5.5.
555. Sorry, there's a 555 timer joke running.
Yeah, that's right. So let's see, this will take a little bit longer to run. So the nuclear spin has an even slower clock speed than the electron for the same reason. Now, what sets that clock speed is so when we apply that radio frequency or microwave signal to the spin, we are creating an oscillating magnetic field. The amplitude of that oscillating magnetic field sets the time scale over which the spin gets rotated from up to down. So if I apply a 1 microtesla oscillating magnetic field at the 39 gigahertz frequency to the electron,
Right.
it's an AM, it's amplitude
AM,
modulator.
yeah.
So if I apply a microtesla, it will give me a 28 kilohertz rate at which the electron goes up and down. So by seeing that that was at was about 200 kilohertz, it means we were running something less than 10 microtesla oscillating magnetic field at 39 gigahertz.
Wow.
Right?
Okay, got it.
Now, with the nuclear spin, because the gyromagnetic ratio is more than 1,000 times smaller, it actually goes much slower. Now, it doesn't go 1,000 times slower because being at megahertz instead of 40 gigahertz, we have much less losses along the coaxial line. So we're actually able to put a lot more power down. So it goes about maybe 100 times slower. So that's right, yeah. So this excitation signal to flip the nucleus is slow enough. You can see it on a simple oscilloscope.
Why is it multi-level there? It was like a trinary level.
Because what you're seeing, so in the process of doing this experiment, he's not only staying at what we call the readout position, but is also moving the gates to a different place. And there the current has a different value. So basically what you want to do here is you want to remove the electron altogether and have the nucleus just there by itself. And as you move, you see most of the time it's two levels, but as you move around, you may hit a spot where the current is some halfway through. But you're not doing any readout at that point.
Take a real long.
Yeah.
I think there's a bug.
Oh, there's a bug in the code. Welcome to real experimentation. There's a bug in a Python code.
We're debugging
It happens to the best of us. It happens to the best of us. So this setup here is quite unique. It contains something that we have developed. So we can run two different experiments in the same fridge. Now remember, to operate a spin quantum bit, you need a strong magnetic field of about 1 Tesla, right? So the device that's down here, you see there is this finger that sticks down, and that's such that when you put the solenoid out there, the solenoid is here, and the center of the field is exactly where the device is.
Right,
Yeah.
it's got to be right,
Right,
in the center.
right in the center. But actually, the coldest point of the fridge is this entire plate here, right? So this is the coldest point, and this is thermally attached to that. Now, in here, we have a second device where the magnetic field is created by an array of permanent magnets. So we took this is a standard design, it's not invented by us, it's called the Halbach array. It's basically an array of permanent magnets that makes a very strong and quite uniform magnetic field in the air gap. And then we augmented that with a piece of a soft magnetic material called supermandur. It's a soft magnetic material, but it has a 2.4 Tesla saturation flux density. And so with that array, you can get up to about 1.2 Tesla in a probably 6-8 millimeter air gap, which is enough for us to put our little silicon chip and all the bond wires and everything. Right? So we can actually run two completely independent experiments, one in the magnetic field created by the solenoid and one in there.
Nice.
Nice. The other nice thing about this is that it's incredibly stable. It's actually more stable than the magnetic field of the superconducting magnet. Remember what I said before is that you have this supercurrent that flows with zero resistance forever. Like everything in this world, it's not exactly true. There is a very slow decay of that. So that magnet, which is a state-of-the-art magnet with a state-of-the-art superconducting short, it drifts about 40 parts per billion per hour. It's a very slow decrease. But the quality of our qubits is so good that we actually see it.
Oh,
It's okay.
I was gonna ask that, yeah.
In fact, we are the ones who told the manufacturer how much the drift is. They wouldn't know how to measure it
wouldn't know how to
otherwise.
measure it.
But because our qubits are so stable, we measured it for them.
Wow.
Right? So that's really important for us. This permanent magnet array is actually better than that. It's less than 10 parts per billion. It's great. It's nice and compact. You know, it's like a very old-fashioned thing to say. It's like big as a pack of cigarettes. Nobody smokes anymore, but you know, that's what it is. And this actually, you can see, it's even a tunable device. So you see there's all the brass box, but you see the sort of silver-colored part here where I'm pointing.
Oh, yeah, you can
That's the
adjust that.
Superman. You can adjust it. There's a screw there, so you can adjust the air gap. And of course, you can't do it in situ. You have to do it before you close off. But if you can tune it between 0.6 and 1.2 Tesla, more or less, with a reasonable air gap. And so on this fridge, we can fit one of them. But there are even bigger fridges where the plate is this big. You could put 3 or 4 of them.
Right.
It's completely independent with their own magnetic field and just run the experiments as independent parts.
Because it's...
There's more stuff if you like. So we've done the...
What do we got?
We've got the nuclear control. Remember the little sinusoid that I showed to you before where we were turning the electron from down to up and so on? Here we've done the same but on the nucleus, not from down to up, but just between a pair of states. And you can see it makes another beautiful sinusoid. How long does it last? This is about half a millisecond, so 500 microseconds for a... So it's about 100 times slower than it was before because of the gyromagnetic ratio of the nuclear spin. But look at the perfection of this sinusoid and how it goes between 0 and 1. The one you saw before didn't go between 0 and 1. We had a little bit of readout imperfection. This one is almost perfect because the nuclear spin can be read out repetitively. So we can remember how we read the nuclear spin? We interrogate the electron. We ask the electron, at what frequency do you respond? And we can do it multiple times. We can keep asking and build up statistics so that we reduce the errors even more.
And you can do error correction at that higher level as well. You don't necessarily have to do it at the quantum level. Is that?
So the error correction involves classical decoding, so to speak. So you remember, a quantum measurement always gives out a classical bit of information. So even quantum error correction relies upon cleverly extracting a classical bit of information from the system, and from that result inferring whether you need to do something about your qubit or not. Right?
Okay.
In fact, that's another interesting aspect of useful large-scale quantum computers. They will certainly need to be coupled to some very powerful classical computers for that purpose, to analyze in real time those quantum error detection signals and apply the correction straight away.
So a quantum computer is not possible without a classical computer?
Absolutely not.
Even
And
the
a good
IBM
one. And a good one.
And a good one.
And a good one too.
Wow.
Yes. Yes.
So even
Yes.
the IBM one's doing that?
All of them. All
Right.
of them. All of them.
Got it.
Every quantum computer needs to be embedded within a very, very, very good classical computer.
Interesting.
Yeah.